Welcome to the improved phase of the Six Sigma methodology. By now, you've completed the analyze phase and have a clearer picture of where process inefficiencies or defects lie. In this stage, it's time to turn insight into action. The improve phase is where solutions are developed, refined, tested, and piloted to drive measurable improvements. The goal here is simple. Implement solutions that reduce variation, eliminate special causes of issues, and improve overall performance. The tools in this phase help teams propose, validate, and refine improvements. Let's walk through each of these tools and techniques in detail. Let's start with the affinity diagram, a creativity tool designed to generate a large number of ideas and then organize them logically. Originating from Japan and credited to Kawakita Jiro, the affinity diagram is also known as the KJ method. It's especially helpful when dealing with complex or chaotic problems. There are 6 basic steps to developing an affinity diagram. Clarify the chosen problem or opportunity in a full sentence. Collect the current data available on the problem or opportunity. This is usually done by brainstorming within a group. Record each piece of data or idea onto a card or post-it note and place them at random onto a board. Sort ideas simultaneously into related groups. Arrange the group affinity cards, usually less than 10 in each group, in a logical order. For each grouping, label header cards and draw broad lines around the group affinity cards. For example, suppose your team is investigating barriers to a quality improvement program. You collect all ideas, cluster them into themes such as leadership, communication, or training, and label them. That's your affinity diagram. Nominal group technique, or NGT, is a great follow-up to a brainstorming session. It helps you prioritize ideas in a structured and democratic way. Everyone votes, items of importance are ranked, and no one dominates. There are 5 basic steps with the nominal group technique. Assemble the team and generate a list of issues, problems, or ideas to be prioritized. This could be done either by a brainstorming session, or each member may be asked to write down their ideas. Write the list on a flip chart or board. Refine the list by eliminating duplicate or similar statements. Assign labels to the final list of statements and record them on a flip chart or board. Each member records the labels of each statement in a rank order with the highest number allocated to the most important statement. For example, if there are 5 statements, then 5 is the most important and 1 is the least important ranking. Aggregate the rankings of all team members, and the statement with the highest point would have the highest priority. As one example, consider the case of a private school where several complaints have been made about the low morale of staff, but they are of an informal and unstructured nature, and the Board of Governors have little to work with. 5 members of the team have allocated a rank order to each problem. These scores are then added to create the total column, and it appears the 2 priorities where most attention should be focused are B, information coming from an in crowd, and D, dogmatic approach of the head. You now know where 80% of your time should be spent. Like the affinity diagram, NGT works best during an actual group exercise. Facilitators guide the team toward consensus. Let's talk about ESS-MED, or single-minute exchange of die, which is a powerhouse tool in lean manufacturing. Developed by Shigeo Shingo, ESS-MED focuses on reducing changeover times in manufacturing. This tool won't apply to all projects in the case of this particular course, but it is a useful tool to know about. There are 5 basic steps to SMED. Study and measure the operations of the production line to discriminate. The internal setup, which is the operation that must be done, or the machine is stopped. An external setup, which is the operation that possibly can be done while the machine is still running. Suppress non-value-added operations and convert IS operating into ES. The data from OEE and the preparations of prerequisites, for example, tools, changeover parts, pre-assemblies, preheating, mobile storage, etc., are reviewed to achieve results. Some internal setups are converted to external setups. The next stage is to simplify the design of the machine, especially fillings and tightening mechanisms. Some examples of the design simplification are U-shaped washers, quarter-turn screws, and cam and lever tights. Balance the work content of the line and ensure teamwork. For example, in one automatic insertion machine, one operator sets up on the machine front while the other operator feeds components on the other side. Minimize trials and controls. Use of mistake proofing or poke-a-yoke enables the standard way to be carried out each time. The following is an example in which the internal and external setup times have been measured. In order to reduce the total amount of setup time, they overlapped external setup times with internal setup times. This is also referred to as a parallel process. SMED can produce excellent results in achieving the reduction of setup times, but admittedly, it is resource intensive. It should therefore be restricted to bottleneck operations. The 5 S's is about workplace organization, cleanliness, and discipline. Originating in Japan, each S stands for a principle. Sort. The initial step in the 5 S's program is to eliminate excess materials and equipment lying around in the workplace. These non-essential items are clearly identified by red tagging. Set in order, the second step is to organize, arrange, and identify useful items in a work area to ensure their effective retrieval. The storage area, cabinets, and shelves are all labeled properly. The objective of this step is, as the old mantra says, a place for everything and everything in its place. Shine. This third action point is sometimes known as sweep or scrub. It includes down-to-basics activities such as painting equipment after cleaning, painting walls and floors in bright colors, and carrying out a regular cleaning program. Standardize. The fourth point encourages workers to simplify and standardize the process to ensure that the first 3 steps continue to be effective. Some of the related activities include establishing cleaning procedures, color-coding containers, assigning responsibilities, and using posters. Sustain. The 5th step is to make 5 S's a way of life. Spreading the message and enhancing the practice naturally involves people and cultural issues. The key activities leading to the success of 5 S's include: recognize and reward the efforts of members, ensure top management awareness and support, and publicize the benefits. These can be applied anywhere from your workplace to your home. One of the best examples I've seen is application to a coworker's house coffee area. By applying the 5 S's, they were able to cut down their morning coffee prep from 5 minutes to 3 minutes. Although seemingly not much time saved, in the long run 2 minutes every day can add up. 5 S's is a simple tool and should be considered for the housekeeping and visual control of all types of work areas, whether they are in manufacturing or service. In this unit, you may wish to apply the 5 S's technique in your project or in your daily life. Poka-yoke, or mistake proofing, is designed to stop defects before they occur. There are 3 basic steps in mistake proofing. Perform Shingo's source inspection at the design stage. In other words, identify possible errors that might occur in spite of preventive actions. For example, there may be some limit switches that provide some degree of regulatory control to stop the machine automatically. Ensure 100% inspection by the operator to detect that an error is either taking place or is imminent. Provide immediate feedback for corrective action. There are 3 basic actions in order of preference. Control. An action that self-corrects the error, for example, spell checker. Shutdown. A device that shuts down the process when an error occurs, for example, a limit switch. Warning. Alerts the operator that some error is imminent, for example, alarm. Consider the situation leading to the development of a level crossing. This is a place where cars and trains are crossing paths, and the chances of accidents are very high. The possible errors that might occur would relate to car drivers, who might be thinking one thing or another, or distracted while driving, or source inspection. Both the level crossing operator and the car driver should ensure safety features while the work is in progress, otherwise known as judgment inspection. In order to prevent drivers from making mistakes when a train is approaching, traffic lights were installed to alert the driver to stop, or also known as a warning. The lights might not be completely effective, so a gate was installed when a train was coming. Specifically, this is a shutdown or regulatory function. The operation of the gate was controlled automatically as the train was approaching, basically a control. With the above mistake-proofing devices in place, an accident can only occur if either the control and regulatory measures are malfunctioning or the driver drives around the gate. Mistake-proofing is a simple tool in principle, but its execution is the difficult. The contrast between mistake-proofing and fool-proofing, however, is critical. The essential difference is that in mistake-proofing, operators are respected and treated as partners in solving problems. Value Stream Mapping, or VSM, offers a big picture view of the production process, showing where value is created and where waste hides. It's where you visually map out each activity in a process to determine waste. There are 7 basic steps in value stream mapping. The first step of VSM is to select the product or process for improvement. Each component of production from the source to the point of delivery is then identified. The entire supply chain of the product or process, for example, through order entry, purchasing, manufacturing, packaging, and shipping, is mapped sequentially. The quantitative data of each activity, for example, storage time, delay, distance traveled, process time, and process rate are then recorded. Each component, that is, activity, of production or process is evaluated to determine the extent to which it adds value to product quality and production efficiency. These activities are then categorized as value added, necessary non-value added, unnecessary non-value added. Areas of further analysis and improvement are then identified clearly. Value stream mapping is one of my favorite tools because a complete value stream map quickly provides the visibility of the total process and is very effective in identifying non-value added activities at a macro level. In this unit, you will watch a separate video on creating a value stream map, which may be a useful tool for you to apply to your process improvement project. The improve phase is the most creative and the most rewarding part of Six Sigma. It's about turning data into decisions and ideas into actions. Here's what you've learned. Use structured tools like the affinity diagram and NGT to shape group ideas. Implement lean tools like SMED, 5S, and VSM to cut time and waste. Apply Six Sigma tools like mistake proofing to reduce defects. Later on in this unit, we will also introduce you to thinking tools, including Stanford's design thinking method. As you prepare to move into the control phase, remember, improvement is not just about finding answers, it's about implementing them in a sustainable, measurable way. Thank you for joining me in this unit. I'll see you in the next one.